As a civil engineering student, I remember one of the first things we got introduced to in uni was calculating internal forces by hand. And to be honest with you, it took me a very long time to understand how a bending moment works. But that's a topic for another time. So, internal forces can only be calculated in the simple way with the three equilibrium equations if the structure is determinate. On the other hand, if a structure is statically indeterminate, then more complicated methods need to be used to calculate moments, reaction, shear, and axial forces. So in this video we'll cover what the difference between internal and external indeterminate structures is, what statically determinate structures are, and the opposite, what structurally indeterminate structures are, and in the end we'll cover determinacy equations. So let's get started. Before we explain what external and internal indeterminate structures are, we first have to mention that when we talk about determinacy and indeterminacy in this video, then we mean internal determinacy instead of external. Alright, so what is external indeterminacy? So if the reaction components can't be calculated, then the structure is externally statically indeterminate. In easy words, if the static system has too many supports. An example of this is the three-span continuous beam, where we have 4 reaction forces but only 3 equilibrium equations. We know that the horizontal support force equals 0, however, we can't solve the 3 vertical reaction forces because we are missing one equation. On the other hand, for an internal indeterminate structure, we can calculate the reaction forces, but we can't calculate the internal forces. This is basically the case when the structure doesn't have that many supports, but the static system is quite complex. For example, this truss, which has 3 reaction forces, and these 3 reaction forces can be calculated with the 3 equilibrium equations. But the internal forces can't, because it has too many unknowns in its nodes when we do the equilibrium equations there. So to summarize, for external indeterminate structures, we can calculate reaction and internal forces, while we can at least calculate the reaction forces for internally indeterminate structures, but not the internal forces. Alright, so what's a statically determinate structure now? Statically determinate structures are structures in which the reaction forces and internal forces can be calculated by the 3 equilibrium equations, which are saying that all vertical loads and forces are equal to 0, all horizontal loads and forces are equal to 0, and all moments are equal to 0. So for statically determinate structures, we can use these 3 equations to first calculate the reaction forces, and then the moments, normal and shear forces. Examples of statically determinate structures are simply supported beams, cantilever beams, simply supported columns, 3 hinge arches, and trusses with hinge connections, to just name a few. Alright, so now that we know what statical determinacy is, let's find out what statical indeterminacy is. Statically indeterminate structures are structures in which the reaction forces and internal forces cannot be calculated by the 3 equilibrium equations. When trying to solve the 3 equilibrium equations for an indeterminate structure, you will experience that you have 4 or more unknowns for only 3 equations. This applies for reaction force and internal force calculation. So for example, a rigid frame with 2 fixed supports has 6 reaction forces, but only 3 equilibrium equations. Therefore, we can't calculate the reaction and internal forces. Other examples of statically indeterminate structures are continuous beams, frames with 2 pin supports, and trusses with moment stiff connections. Next, we will look at how we can calculate whether or not the structure is statically determinate or indeterminate. Okay, so the degree of indeterminacy D for beams and frames is calculated as D equals 3n plus r minus 3j minus c, where n is the amount of members, r the amount of external restraints, or also the number of support reactions, j is the number of joints, and c is the number of releases introduced, or also internal hinges. And if D is greater than 0, then a structure is statically indeterminate. Okay, a lot of theory, let's apply this to some examples. First example is a 3-span continuous beam, where we say, okay, the amount of members is 3 because we have 3 bars. R is 5 because we have 1 horizontal reaction force and 4 vertical reaction forces. The number of joints equals 4, and we have no internal hinges, so C is 0. When we put that in the formula, we get D equals to 2. And that means that the structure is statically indeterminate to the 2nd degree. And the reaction and internal forces cannot be calculated by the 3 equilibrium equations. Let's look at another example. A 3-span continuous beam with an internal hinge. We can again define N equals to 4 because now we have 4 bar elements. R is the number of support reactions. That's still the same. It's 5. J is the number of joints. Now we introduced 1 more joint, so it's 5 now. But C stays the same and it equals to 0. Now if we plug that into the formula again, we get D equals to 1. And that means that the structure is statically indeterminate to the 1st degree. And the reaction and internal forces can still not be calculated by the 3 equilibrium equations. And we would need actually another hinge to make the structure determinate. Alright, now for trusses there is actually another formula. Let's have a look at that one. The degree of indeterminacy for trusses is calculated as D equals N plus R minus 2J, where N is again the amount of members, R the amount of external restraints or the number of support reactions, and J the number of joints. Let's look at the Laurin truss, where we define the amount of members as 11, the number of support reactions is 3, and the number of joints is 7 in this case. If we plug that into the formula, we get D equals to 0. And that actually means that the structure is statically determinate and that the reaction and internal forces can be calculated by the 3 equilibrium equations. Let's look at another example, the Howe truss, where we again define the number of members, bar elements, that is 21. Then the number of support or reaction forces equals to 3 because we have a pin and a roller support. And the number of hinges equals to 12. Now if we plug that into our formula again, we get D equals to 0. And that means again that the structure is statically determinate and that the reaction and internal forces can also be calculated by the 3 equilibrium equations. Now that you got introduced to statically determinate and indeterminate structures, it's time to calculate internal forces in one of the next videos. So stay tuned. Thanks for watching, and if you enjoyed this video, please give it a like. You can also find other structural engineering guides on our homepage, structuralbasics.com. Until next time.